So we will be recording this webinar.
Yeah.
And yeah, so and we will be, making part of our library. So which share with our members who are, you couldn't attend this particular webinar today.
Yeah. So it's nice to have the recording too, because then if you have something to go back on, you can fast forward into the specific location or look at the slide deck and pause it instead of having to take screenshots every time.
Sure.
And I'm happy to share the slide deck as well.
Yep. Sachin, can you make Saurabh the host so that he can share the video? Sachin?
Sachin? I think Sachin is muted.
Okay. Sachin, आप सौरभ को host बना दीजिए so he can share the video for SigmaWeld and then we'll start.
You start. अभी वो PPT check कर चालू करेगा.
ठीक है. Okay. Then Dr. Krishnan can introduce the speaker and then we can start.
Yes. After Saurabh presentation is over, Dr. Krishnan.
Yeah.
Then we can start the
Sure.
meeting. Saurabh.
Okay. Saurabh.
So sorry,
Yeah.
it's showing how disabled participant sharing screen. It's showing.
Saurabh, क्या हो गया?
Sachin, you have to make Saurabh the host. I think you have made me the host by mistake.
So अभी एक बार नीचे ठीक है मैं वापस चेंज करता हूँ.
हाँ.
सौरभ अभी चेक करो. सौरभ.
Checking, sir. Okay. Just a minute. Yes, sir.
Okay.
Yes, sir. Just a minute.
Please start your presentation.
होता नहीं है वेल्डर रिलेटेड प्रॉब्लम है अगर ऐसा कुछ नहीं होता है सर्विस ओवरऑल देखता है.
I think we need to mute all. There are some other voices coming.
से बात करते हैं.
Saurabh, we are not able to hear anything, huh?
Yeah, there is no voice, no audio.
Okay, I'll quickly take over then. Saurabh, there is no voice. This is a quick introduction to electronic devices, our company, which owns SigmaWeld, the brand. The company was established in 1974 in order to produce import substitute equipments in India for induction heaters, dielectric preheaters. And in 1981, our first product of dielectric preheater was established and launched. It was used for preheating any kind of dielectric materials such as bakelite, melamine, gun butts, and things like that. Likely dielectric preheated by us. And if you are born before the 1990s and you have seen the black telephone box, it was a good chance that it was molded using our dielectric preheater. In 1989, we came up with a concept of induction sealing, which is the plastic packaging automation wing that we have. So if you look at an aluminum foil seal in any bottle, chances are we have done that for almost all applications, right from food, pharma, lubricants to all. And then in 1991, we had a JV with an Italian company for medium to high frequency induction heaters. We eventually take over that company and we today export to more than 80 countries. Induction heaters and induction sealers for various applications, including pre-weld, post-weld heat treatment, hardening, annealing, forging, shrink fitting, many applications. Early 2000s, we established our R&D department, which today is the Government of India approved DSIR registered laboratory. We have our own brand of welding inverters that we designed and launched in India called SigmaWeld. These are the range of digital welding inverters for all applications of Arctic mix submerged arc and automation solutions related to that. In 2010, we expanded our base from Mumbai to a place in Gujarat called Umargaon. And now, as on today, we have more than 6 patents and many are under defense. Another 4 are under defense. And our company is government approved R&D laboratory as well. And we have exports to more than 80 countries. Saurabh, next slide, please. So in just for electronic devices, we have about 287 employees today. We have got more than 10,000 customers and exports to over 80 countries. Saurabh, can you fast forward? Yeah. Furthermore, yeah. So a few contributions of SigmaWeld. So the 2 Chandrayaan-1, Chandrayaan-2 solid fuel boosters were welded by our automation solution. For the Gaganyaan, that is the next first man-based solution that India is giving, man-based mission. The heat treatment of the semi-cryo parts is being done by us. Titanium bundle welding for all the nuclear submarines that guard Indian waters are also done on our solution. All locks and safes made by Godrej are welded using SigmaWeld. We have contributed to NPCIL for N-Shield automation. We've also done successful remote repair of the BSC system repair for the PFBR using internal bowl and orbital TIG welding process, which was custom built by us. Of course, more than 10,000 equipments working with over 1,000 MSMEs across India, helping them build the nation faster. Few awards that we've been given, the top one being the best technical paper. The one on the bottom is the Made in India award. The one on the right is being issued by the governor of Maharashtra. That was the Pride of the Nation award. And the one on the bottom is by Jitendra Singh, the Minister of Technology, awarding us the National Technology Award in 2023 for the most innovative MSME. Later, we were also awarded by the Economic Times Group as the most innovative MSME in the medium sector for the year 23-24. That's a little bit about electronic devices and SigmaWeld. We are in sources and automation solutions for various applications of Arctic mix submerged arc and automation solutions. With that, I would like to thank IW for this opportunity, and I would like to pass on the host to Dr. Krishnan so that he can introduce our guest for today. Saurabh, you can stop sharing.
Yeah, thanks, Nimesh, for the brief introduction regarding Sigma. And we are on behalf of IW, we are so thankful that you have been supporting this Weld Tech Talk for the last couple of years. So today we have a very interesting talk by Ms. Cameron on a practical approach to successful production welding. I'm sure it's going to be a very interesting topic. And she is a BSc in mechanical engineering with specialization in materials from the University of Windsor in 2016. She is also a practicing engineer in Alberta and Texas. She is a very active member of ASME Section 9, various task forces, and a very active member in the American Welding Society as well. And she has a decade of welding and metallurgical engineering experience, especially in the petroleum industry, including design, new construction, maintenance, and most interestingly, the turnarounds, which we all know it's a really challenging experience to handle the problems which comes and you need to decide and give solution on the spot. So she has worked for Canadian Oil and gas owner users in central engineering roles and critical assignments. She has also worked as a consultant supporting both domestic and international clients, various fabrication shops, and the list is endless. So it is really our pleasure to have Ms. Cameron for today's webinar. Please, ma'am, it's over to you.
Thank you. All right, let me share my screen.
So we have almost 140 participants as of now hearing you.
Oh, that's awesome.
Yeah.
Hopefully it goes well. Let me do, here we go.
Sachin, you have made her the host?
Yes, she is a host now.
Yeah, okay.
Yeah.
Yeah, your presentation is visible. Yeah.
All right, sounds good. Like I said earlier, I could go on and on for hours for this, but I've been limited to about 45 minutes to an hour. So
Yeah.
I'm going to go over some very high level items. And if anybody has any specific questions or whatnot, feel free to ask in the chat and we can, progress through the
Yeah, we can
presentation.
address it towards the end. Yeah.
Awesome. Perfect. So as everybody mentioned, these are the practical approaches for successful production welding. And I appreciate y'all for letting me be here. I'm very excited to present. All right, now if I can work my controls. Okay, so today we're going to talk about welding. What is it? I'm sure a lot of these things are going to be review for you, but perhaps not. We're going to go through what I call meet the team, basically weld procedures, PQRs, and WPQs, or welded performance qualifications. We're going to go over the welding processes and the intentions of the welds, typical challenges in industry, leading into why welding locations are important, welders, that they do actually matter and is very important for the application of production welding. We're going to go through the applications of weld procedures and PQRs. We're going to touch on a practical approach, a specific case study on that. We're going to dabble in some heat input and how those are very important. And we're going to go over some heat treatment and we'll go into a summary on there. I'll mention about 95% of these photos, if not more, are my own. From various jobs. I can't disclose specifically what companies they are, but there's lots of very interesting photos and schematics as you will see throughout the presentation. So welding, what is it? These definitions predominantly come from ASME Section 9, which is the American Society of Mechanical Engineering. Section 9 is the welding standard and code. So if anybody is interested, or most people are likely familiar with it, if not, I can give a list of all the references and everything at the end of the presentation as well. So a weld is a localized coalescence of metals or nonmetals produced by either heating the materials to the welding temperature or with or without the application of pressure, or by the application of pressure alone, and with or without the use of a filler metal. Essentially, welding is rapid heating of materials to their melting point, then a rapid cooling to ambient temperature. A mentor of mine many, many years ago had said, a weld is just a very small casting, and can be layered casting on there. So it's a very different way of looking at a weld. A lot of people can look at this as it's a very intricate piece of joining predominantly metallics, but at the end of the day, it's a very small casting without a mold or any of that. So it takes a very specific operator or welder to manipulate that casting to do what you want it to do, or on the flip side, not do what you want it to do. So we're going to go over meeting the team. I've gone over a few examples of this where I like to use a reference that a welding is basically with the use of a weld procedure, PQR and a WPQ, is like baking a cake. So instead of the recipe, we're going to be using a weld procedure, because that is exactly what a weld procedure specification, or WPS is what I'm going to be calling it going forward, is essentially a recipe of how you're going to be conducting the welds. It's like if you go on to online and you pull up a really wonderful recipe, or perhaps you have something hidden away in the cabinet, or your auntie or mom or whoever has a recipe in their head that you make them all the time. It's the same emphasis for welding. You need to have a specific list of ingredients, as well as a step-by-step guide of how you're going to be completing the recipe or the weld. By definition, a welding procedure specification, or WPS, is a procedure specification which is written as a written document providing direction to the person applying the material joining process. Again, pretty straightforward. It's a list of instructions with the ingredients of how to complete the weld itself. When you get into procedure qualifications or PQRs, this is essentially that somebody has done and followed the recipe. They have followed the weld procedure, the WPS, and showcased that it's actually doable. There's lots of recipes out there on the internet, or perhaps you've even tried to follow a recipe that you know works. And when you've done it, it hasn't been very successful. And it happens more times than not. I've got a really cute picture of Martha Stewart. I'm not sure if she's super popular in y'all's area of the world, but she's quite popular in North America. And here it's basically a description of saying, hey, yeah, this is what you can do with your weld procedure or your recipe. So the procedure qualification record is a demonstration of those mechanical properties of the joint made using a joining process, and not the skill of the person using the joining process. That's a very key difference. It essentially just saying the recipe works, the weld procedure works. You can get the appropriate, in this terms, mechanical properties, such as tensile test, toughness, rigidity of the joint. You want the weld to stay together, it's usually pretty important. But that recipe or that weld procedure actually functions. Somebody has tested it destructively in most times that it's actually doable and gets the result that you want. The final one is going to be the welder performance qualifications, or the WPQ. That is a qualification of the person who will use the joining process to demonstrate that the person's ability to produce a sound joint when using the procedure specification. So on that sense, you're basically saying that now you've got the recipe, somebody has tested it out saying that, yes, the recipe works. Now it's time for you or the welder or whomever is going to be performing the actual job can do the work. Again, this is in a test function, so they actually go through and complete a test, and that is then destructively tested to make sure that they pass the requirements. In section 9 particularly, it falls under visual inspection as well as bend test. Now that's the bare bone basics. There are a number of other places that will utilize additional testing, such as hardnesses or toughness, Sharpies or whatnot. But again, that's above and beyond the code and not always applicable. There are times and cases that you want to utilize those, but not all the time. In this particular case, there's a really nice test, which is a weld test, but this is a restricted one instead of your typical open an area where they have a lot of movability and space on there, which can come in very handy, as many of you know who have been in the turnaround situations or have been specifically in furnaces. It's not the easiest place to get into. So welding processes, again, a lot of these are probably going to be reviewed for you, but we'll delve into the details anyways. So shielded metal arc welding, or SMAW, otherwise commonly known as stick welding, is an arc process with an arc between the covered electrode, or a rod, some people will call it, and the weld pool. The process is used with a shielding from the decomposition of the electrode covering, without the applications of pressure, and with a filler metal from the electrode. It's a very rudimentary welding process and manual in nature, where gas tungsten arc welding, sometimes known as TIG or heliarc welding, is an arc welding process which produces the coalescence of metals by heating them between an arc between a tungsten, which is the non-consumable electrode, and the workpiece. The shielding is obtained from the gas or a gas mixture through a nozzle on the nozzle itself. Where SAW, or submerged arc welding, also known as subarc, is a welding process that uses arcs between a bare metal electrode or electrodes, depending if you need one or two, and the weld pool. The arc and the molten metal are shielded by a blanket of granular flux on the workpiece. So in this case, it's a very interesting welding process because you don't see the actual arc itself. Gas metal arc welding, also known as MIG welding, again, is an arc welding process that uses an arc between the continuous filler metal electrode, the weld pool, and the process is used with a shielding from externally supplied gas and without the application of pressure on there. I'll note that a number of these do have different transfer modes. Particular GMAW has a couple options off of there, but we're not going to dive into those specifics right now. And finally, we're going to touch on flux core arc welding, also known as flux core, is a gas metal arc welding process, so similar to MIG, that uses an arc between a continuous filler metal electrode and the weld pool. This process is used with the shielding gas from the flux contained within the tubular electrode, so slightly different than MIG, which is a solid wire, and stick, which has the flux on the outside. Well, the flux is contained within the tubular electrode and it is used with or without the addition of shielding gas from externally supplied gas and without the application of pressure. I'm not going to go into the details of any more higher level types of welding processes. We're going to kind of stick to the main better. So if we want to talk about laser welding or any of that, that'll have to be another day. Here we have some really cute examples of these specific processes. So as you see here, we've got stick welding. He's got his stinger and he's quite open in the area. Doesn't have a lot of restrictions in terms of space. Stick welding is one of the more usable and easiest to get in and out of specific areas. It's also very easy to set up and you can put your power source anywhere on that aspect. And we'll touch on that afterwards. Here's a photo of TIG welding or gas tungsten arc welding on a heat exchanger. As you see, it might be a bit challenging to see on here, but you can see the wire, the straight wire in there, and he has a torch which is kind of led through in here, which obviously you can see if you've got a large wire, which you can cut to size, but that limits the amount of filler metal that you can add to it. Can be a little challenging in tight spaces, doable, but challenging. And here we have a picture of a sub-arc machine or a submerged arc welding machine. You can see here, and I apologize because the photo isn't as clear as it was on my screen, but you can see the flux and you can see the arm that goes through there and the heat, the weld pool underneath the flux, which is very interesting. Here we have gas metal arc welding. As you can see, there's quite a bit of a nozzle off of here, as well as we would call it a gun or a welding gun, which, as you can tell, may or may not be difficult to get into specific tight spaces. And then finally, we have a picture of the flux core, very similar in nature to the MIG welder, where you've got quite a sizable gun on here. Again, very similar. You may or may not have challenges of getting in or out of locations. So a really important thing when it comes to the actual practicality of welding is what are your welds intended for? You know, do you have a specific code of construction? Is that known? If not, you should probably figure that out. That becomes very important when you're actually completing your welding. That dictates what your weld procedure requirements, your PQR requirements, your welder qualification requirements, from a bare minimum or above and beyond. All of these additional testing requirements, very specifics on welder technique or weld procedure techniques. And on there, it's very, very important to know what the code that you're actually welding to. Most places here in the States and a few other places, it's governed by ASME, or the American Society of Mechanical Engineers. Those can follow under ASME Section 8, predominantly Div 1, which is vessels and heat exchangers on that sense. B31.1, which is going to be power piping, a lot of boiler piping and all that. B31.3 is going to be your process piping. So it could be anything from, you know, plain Jane water to very lethal service or carcinogenics on there. Then in Canada, we have CSA W59, which is a structural welding code. So bridges, beams, buildings, all that jazz on that sense. There's also Z662, which is a pipeline in Canada as well. In the States and a few other places, they use API 1104, which is also a pipeline standard. It has a whole different slew of requirements from ASME itself. So it's very important to know which you're using. You can't necessarily use something that's appropriate for ASME that works for 1104 or Z662. And then AWS, which is the American Welding Society, D11, which is structural welding as well. Now there's a lot of overlaps between the codes in different areas, countries, etc. But there's a lot of things that can be vastly different. ISO, and I'm not sure if you'll use a lot of ISO specs, has a lot of cross-fertilization, but there are some slight differences, and I'm not going to talk about that specifically today. And there's a plethora of many, many more. These are just kind of the high level ones. Additionally to your code of construction, are there specific standards or recommended practices that are to be utilized? And here in North America, we use API, or the American Petroleum Institute, a lot. 577 is everything to do about weld procedures, PQRs, welder quals, specifics for in-service welding or hot tapping, which can be quite challenging at best. API 582 gives a lot of guidelines for refineries in particular. They are starting to outreach to go more than just petrochemical and refineries. They are dabbling in some power generations, specifically with P91 and P92 grades on that, which is very exciting. And then we also use the Association for Materials Protection and Performance, which is short form for AMP, and formerly NACE. They've now merged a few years ago back. So specifications like MR0175, which goes over the requirements predominantly for sour services, which include, hardness requirements, specific welding techniques, post-weld heat treatments as well for a few of these, and all that jazz. I put some really interesting pictures in here, and this was from a vacation that I ran across, and we went to a little farmer's market, but as you can see here, it says the boiler house. Back decades ago, this particular place used to be an actual boiler house. As you can tell now by the umbrellas and the few folks that are in there, it's been now converted to a restaurant, which was very interesting. And they use a lot of these older vessels for planters off of here. And that's one thing that you never know what your welds are going to be repurposed for. Obviously, these were quite successful at their job at the day whenever they were utilized in the boiler process. But now we're sat out to go be planters for herbs and spices on here. This is a very interesting weld here, like we would call it a butterfly effect of cellulosic welds, or 6010, which is no longer allowed due to specific reasons, but I thought it was quite interesting in nature that this was still prevalent. This was the first time I've ever seen one in the flesh. So just a very key point to know, where are your welds going, or what is your equipment going to? They can be intended for something like severe as a pressure vessel, or they could be something that's very simple for an herb garden. Going into what are your welds actually intended for? These are their specific internal requirements. These are typically tighter knit requirements based on previous learnings. A lot of those come, unfortunately, from failures, and hopefully not life-altering failures or aspects on that sense, or in a safety or reliability aspect. But typically they are, unfortunately, things that have failed catastrophically or have caused catastrophic effects to individuals or the environment. And when they go through failure analysis or post-mortem assessment, not always, but sometimes you can pinpoint specific reasons or potential additives to the reason of the failure, such as, the welding technique, stress risers, inadequate heat treatments, inadequate control for your specific bead placements, especially when it comes to bead sequencing for temper bead applications or any of that jazz. So very important to go through what are those specific learnings or requirements off of there. If it's been known that, for example, those butterfly cellulosic welds in certain applications have lasted the test of time, so to speak, 40+ years, it's typical industry lifeline, or do they fail every year, every 6 months? It's like, okay, why are we doing that? We don't want to have those failures typically. So how do we prevent that? Can we control that from a welding standpoint? And the answer isn't always yes, but a lot of the times it is, which is really neat. Because you can control a lot of those things and have influence on the success of reliability and safety of a weld mat, be it something as simple as a repair or something as very sophisticated as SigmaWeld had put in there. A lot of the nuclear facility is very, very, very important in those applications. go over again, what are the applications or the service, as we mentioned prior? Is it going into a boiler house? Is it going into nuclear facilities? Is it going into power generation? Is it going into refining, agricultural, etc.? Or is it just going to structural components, which can be very important as well, such as bridges? Or is it just kind of a hobby project or an art piece? We do get a lot of those aspects as well. So you really want to understand, like, what is your application? When it comes to specific services, your welding procedures, your PQRs and your welders may have, as I mentioned prior, additional requirements. That MR0175 talks about sour service. There's additional requirements for hydrogen service. I know that's a really big boom word or fancy word right now in worldwide, and getting hydrogen on the market, and lots of subsidies and research and development and being piled into hydrogen pipelines and all that. And there are specific requirements for welding on that. Stress corrosion cracking, and there's a variety different of kinds of stress corrosion cracking, or SCC for short. Amines, caustic, as an example. High temperature applications can have a whole other slew of requirements as well, even to the sense of specific base metals are really important. You can't necessarily use your, boilerplate or off-the-shelf carbon steel in very high temperature applications. And there's a wide amount of materials that are specifically made for high temperature applications on that sense, that interestingly enough, a lot of the times don't perform very well at ambient temperature. So that kind of takes a very interesting precedence we'll talk about in the procedures afterwards. Also, cryogenic services, the opposite of your high temperature, can have its own challenges in that sense as well, especially when it comes to impact testing. And again, there's a whole plethora of different services on there. These are a lot of the specifics on here. This particular piece of equipment, which you've seen a photo in prior, there was sizable cracking, and this was a platformer reactor, I believe. And there was cracking on one of the manways in particular. A temper bead approach was taken on this. Again, you really need to be cognizant on the procedure used and the welder itself. You can't just go in and fill her up, boys and girls, or whatnot. We had to have a very specific sequencing of the beads and understanding that you're getting the tempering effects to avoid that post-weld heat treatment in this particular case. Now, if that type of cracking happened out on your water trough for your livestock, would it matter as much? Probably not so much. At that point, you could probably just slap some JB Welder bells on it, who knows? All right, so going into typical challenges in industry. Here we find a lot of issues on, your weld procedures particularly. A lot of weld procedures in the IFC, or issued for construction era, can sit and just send out, hey, we're welding this to this, here's a procedure. Not having that specific understanding of what those weld procedures are going to be utilized for, in terms of thicknesses of base metals, the applications of it, such as the services or intentions of it, as we just chatted about, specific thickness requirements, heat treatment requirements, how they're actually going to be conducting the weld. In particular, this is a very interesting photo. I can't talk about the specific details, but as you can tell, a catastrophic failure did happen here. And for those of you that are very familiar in the repair world, I hope that you are internally screaming, because this particular situation, it was quite horrific. You can even see from this aspect, and I'm not sure if you can see my mouse or not, but you can see on that vessel in the first left corner that the welds are quite, and I'm going to use the word ugly in nature from there, and they're very square. In this particular case, when we went through the assessment, the weld procedures were submitted, and it was just a typical carbon steel to carbon steel. They said these are the thicknesses that we're welding. Okay, no problem. However, the application of it was not appropriate in nature, as you can tell on there. So very important to understand where your weld procedures are going to be utilized. I know I've mentioned this a few times, but it's very, very, very important to understand the difference of what you're welding on something that can be very simplistic as a simple piece of art to go hang in your garden or whatnot, to a pressure vessel or nuclear reactors. Other items can involve like the less suitable welding processes for the specific job. You'll see in the top right photo, these are structural components on a FCC reactor. Structural in nature, yes, you are welding onto a pressure boundary though. In the design phases, what had happened was these are clips to support an external structure to help with clearing the cyclones, if anybody's familiar with that. We'd call it lancing in nature. But as you can see how they wanted to go and put them around the entire reactor, there was a size issue. If you recall back in our welding processes, it is going to be very challenging to get a MIG or a flex core welding gun in that small space. I had a hard time fitting my hand in there, and I'm not a very large woman by any means. So let alone getting a whole nozzle in that was quite challenging. This was part of a mock-up to determine if we can actually do the production welding on the actual pieces of equipment in the field in our central maintenance shop at the refinery I was working at, which was very, very important and very nifty to do. I'm a big proponent of completing mock-ups when you do have sophisticated or, people are uneasy with a specific job, because you can showcase that the job is actually doable or disprove that it's not doable and come up with other solutions of how you're actually going to be completing the welding on here. So looking at your specific job and understanding, what processes are going to work or not work. Obviously, in this case, sub-arc is not going to be very appropriate in that, but you would be very surprised, and I'm sure many of you are nodding your head currently on how many people want to sit there and use sub-arc or use these odd processes for jobs that don't quite make sense. Other things that can be very challenging at best is when you don't have real estate or area in your facility to put your power sources or run cables. And we'll talk about that in the next little bit. Preferred consumables. Again, this seems like I'm reaming on this, but without the application or service knowledge, there are specific requirements for specific consumables, predominantly either gases or filler metals. 6010 in particular is not very good for sulfidation or naphthenic acid services. It will just eat the root out completely, and you will have crevice corrosion, and you can cause a number of premature failures. I've dealt with that quite extensively in the DRUs, in particular in the refining nature. Very, very important. Specific requirements for low or high carbon contents on consumables can make or break jobs, especially when hardnesses are important, or even indirectly toughness requirements. Leading into toughness requirements, there are specific consumables that will meet your toughness requirements and others that will not. Depending where you are, for example, or what your ambient temperatures are, that can be very, very important. I know India is a very large country, and I believe you do have mountain ranges in there. So areas in high altitudes that you do get a lot colder temperatures, and I'm not sure the exact temperatures of what you would see, but I come from Canada and I worked up in northern Alberta, which sees -40 degrees centigrade for months on end. It's very important. Where if you go through and you're working in the Gulf Coast of Mexico, where I now live in Houston, those low temperature applications may not be that important. So be very cognizant of what those consumables are, how they're going to be utilized. Making sure that you have the right welder for the job. I use this all the time, and I forgot to put my beautiful picture of a Picasso. Not everybody can weld a Picasso. Picasso was Picasso, and he was able to practice and do his paintings quite beautifully and different in nature. Now, just because you have somebody that sits there, looks at the painting, studies it, could study that for years on end, he or she may still not be able to produce that Picasso identical. Maybe they can, maybe they can't. And that holds true with welders as well. It's very important to know that just because you've done a mock-up in the shop, as those clips that you see on the top right-hand corner, doesn't necessarily mean that the welder who did that in the shop translates over to the different welder that's going to be actually doing in the field, or welders that are doing in the field. Never put all of your eggs in one bucket. There's a varying range of skill set for welders and any trade in that particular case. So making sure that if you do have those critical jobs, that welder has been trained before, they can do the job, either destructively tested or non-destructively tested. Just because they have a welder ticket doesn't necessarily mean that they can do the job. We're finding right now, especially in North America, with the shortage of welders, that people are just getting thrown at jobs and they may not have the skill set to complete that. Lack of communications and collaboration, very important, especially in the evaluation field when you get IFAs issued for approvals and IFCs issued for constructions, and then the actual, construction or execution standpoint for those execution folks or who sit there and work in the actual execution field in engineering or quality sense. It's very important when you're doing those reviews or even scope reviews that you communicate, hey, this isn't applicable. You can't fit a nozzle in there. Subarc doesn't work vertically in most senses. You need to sit there and raise your voice and say, hey, this is right. And not in a condescending nature, but just as an informational aspect. It will make the job go much, much smoother. Leading into also that comes into your experience and skill set that kind of ties into the welder. Not always just the welder's responsibility, it's also their foremans, their general foremans, or any level of management or leadership in that sense, the quality assurance, the quality control, the engineering, welding and metallurgy or materials, as well as the mechanical designers. Very, very important that it's not just paper pushing in a sense, and you actually understand what you're doing and why you're doing that. So where is the welding taking place? This may seem like a very, very simple thought process, but it becomes very, very important. Here on the top left hand, you will see a welding shop that has many bays and booths in there. Welding shops can be wonderful for specific jobs. In this particular case, these are obviously going to be quite small in nature jobs, as you can tell by the size of each of those booths. Where the bottom right hand, you see booths in there, a booth in there as well, but you see that this particular component is out in the open. It's on rollers. There's lots of space in there. So you can sit there and understand, okay, this is in a shop, fantastic, but do we have all this open space to do this work, or are we in a very constricted or restricted area to do the work? Very, very important. You'll also see on the bottom left-hand side, it's a photo of myself inside a stripper column. And as you can tell, again, I am not a very large woman, but that is a very, very tight spot. There was a number of weld repairs that needed to take place on there. So looking at the other two shop components, the one that has the nice arid area versus the one that has the restrictive booths in particular, then you go into further sense inside a very small diameter tower that is very high up in there to go and complete those repairs. Very, very important on that sense. That can make or break a successful weld. Now, when it comes to applications, you may not always have the choice to do it in the nice, comfy, temperature-controlled, spacious shop, and you might have to, and a lot of times you're going to have to be in those very tight, restrictive areas, as you find myself in there completing a weld repair. Location, location, location. Very, very critical. A lot of people don't take this into consideration. Again, it seems very intuitive in nature, especially when you're looking at particularly the slide. Oh, are you doing it in a shop? Oh, are you doing it in the field? Awesome. Okay. But do you sit there and think about that? Do you understand what the applications of that procedure is going to have on restrictions or not have restrictions on the welder, on the ability to inspect it, the ability to make sure that it's actually going to be a mechanically sound, rigid joint. In the shop, you really need to be cognizant if you have different areas for ferrous and non-ferrous welding. A lot of people call that the white shop or the white area. That is very important for materials such as duplex stainless steels, some other nickel alloys and all that, titaniums, zirconiums. Very important that it's segregated. If you have in the shop one bay that has, white welding in particular or alloy, and you have, low alloy chromes adjacent to it that may sound like a very silly aspect, but you can have a lot of contamination between the two, which can make or break those welds in the field. And it may not show its ugly face immediately once you do your inspections, but it's likely on the run, unfortunately, that can cause those. And if you're very fortunate, you can catch it on a turnaround or inspections or routine maintenance, but not always. In the shop, as we mentioned on the prior slide, are you working on rollers? Is the component fixed? Are you not able to roll it? Are you able to roll some components, but not others, especially when you're getting to piping components where you can do some on rollers, but when you start adding on all the additional bends, elbows, reducers, etc., that might not be applicable to roll it. So you might have to look at that on a multi-sense. We can roll this section, we can't roll that section. Can you do them separate? Can you roll these two on separate ones and then make a joining weld? Things to consider that can make or break your actual welding process. As we discussed, is it a bay? Is it booth? Is it in the wide open? Do you have a big plot plan in your shop? Those things, again, things to think about. Not a lot of people will sit there and like, okay, my weld procedure, I've got that. My welder, I've got a qualified welder. We've proven the weld procedure is appropriate. Awesome. We've looked at the service requirements. Fantastic. We've selected the shielding gases, we've selected the filler metals, fantastic, base metals and all that. But now we only have the shop that was selected only has a itty bitty little spot. What are we going to do on there? Now that may put a project on hold for hours, days, months, etc. And nobody likes a project on hold, especially the people or the beam counters. When it comes to the field, things we don't typically think about, again, like weather conditions. In this particular photo, this is out in West Texas on a pipeline. In particular, you can see that it had to be dug out in this component, and it's quite hot. You can get a lot of humidity in there, which can cause challenges to actually the welding itself. You may have to sweat out the equipment. You may not. It can be very dry in other instances, which you can have the potential for static electricity, something not a lot of people think about. Also, is it raining? Is it raining on a specific day? Is there snow? Obviously not in West Texas, there may not be snow, but in Northern Alberta, in Canada, and various areas in the Northern Slope, there's snow a lot of the time. How do you sit there and deal with that? What if you're on a job and it's heavily snowing, sleeting, raining, hailing, etc., you name it. I myself have been in a lot of those job sites where you have to deal with those. So putting up a hoarding or a hooch or a temporary protective barrier may be appropriate, but if the wind is roaring or if it is extremely pelting with rain, or as we would say, raining cats and dogs, that may not be enough. And you need to make sure whatever you're doing is going to be enough, especially if it's a critical job, such as a hot tap or an in-service weld or something that's going to be quite detrimental to the production of whatever you're doing. Internals also very important. This is again in an FCC reactor. We would call these plastic hinges is what he's welding on. They're not plastic; they are metallic in nature. But do you have confined spaces? Is it a cramped space? This particular job is quite fortunate because he does have the flexibility to move around, but you can see all the chain falls that are attached to that specific job, which tells you that there's a lot of tension or misalignment on that specific joint itself. In terms of confined space, as we saw on that picture of me inside the tower, how are you going to sit there and move around? Welders need to be able to sit and articulate and move their rod, move their wire, move their nozzle on that. If you're stuck to a very specific location, that can be very challenging. And you really need to sit there and assess, like, how are you going to be completing that weld? What are the PPE requirements? Do you have a full face mask on? Do you have a half mask on? Do they just have a welding shield? Do they just have a pancake? What do they have on? Because that, again, can sit there and restrict the welder's viewpoint on there. Fallerex, Tyvek, etc., all the other PPEs can restrict those applications of actually physically moving around, completing your welding. Again, a lot of things people typically don't think about, but make a big difference. Us sitting in the office behind our screens, typing away, looking at the drawings, reviewing the weld procedures, quality programs, etc. is one thing, but how the actual people completing the work is a whole other ball game, and that is very important to the successfulness of your welds in itself. Externals, where are an external? Here is this is a top part of a steam methane reactor, I believe, the top portion. Is it on top of a high tower? Do you have scaffolding? Do you have proper walkways in this case? Do you have to get there by crane or JLG or a man basket? Again, fall arrest, open areas. How much movement is there on the piece of equipment? Is it windy? I have been on many cranes and man baskets at very, very high locations, and you can feel those suckers move. Now try doing that in a very specific application of putting a weld bead or that very small casting on there, tied off in a man basket that's moving and your components moving. Again, things to consider on that aspect. So let's talk about the welders. Again, we're diving into the experience and skill level of the welders particularly. I'm not sure about on the international stage, but again, there is a very big gap in North America on welders itself. I believe, excuse me, the average age of a welder right now is 55. And here in the US and Canada, typical retirement age can be 55 to 65. You do find the odd gentleman, mainly gentlemen, but women as well, that will, stick it out to their 70s. I know a few of them, and they are tough as nails. But a lot of people will retire, and if you're not having the appropriate training for the younger generations, you may not get the same output. You'll hear, well, we've done it before, or we've always done it this way, or, where's our golden arm, or, whatnot. Well, those people may not be available any longer, or have they got paid more to go elsewhere in a more comfortable job? That happens all the time. So you really need to sit there and understand what is the skill level, not always necessarily experience, because you can have 10 years of experience, but 1 year 10 times, and them not be awesome welders or very skillful welders. You want to understand what is the skill level of your welder, and that's where just having that ticket of your WPQ or your welder qualification, your welder qual, doesn't necessarily mean that they're the right person for the job. A lot of additional destructive testing or mock-ups can be applicable on that, especially when it comes to very sophisticated repairs or very important new construction implementations. Your general boilerplate, you may or may not be as applicable. How many welders are on the job? Is it a whole big job, or how many welders on the same weld met? In this particular case, and I don't know where my little animations are on this, there's 2 welders, and it looks like a QC gentleman. I had little animations that were supposed to pop up on there where one was saying, oh, I'm so full for my lunch, or I can't wait to get to lunch. The other gentleman who's welding is saying he's very concerned about, not busting his weld or having a failure or an indication or a weld defect pop up. And the inspector's saying, hey, y'all need to hurry up, rush on this job. So what is the vibe of those welders? Are they focused on it? Are they not focused on it? It sounds very silly, but again, welding in the manual sense, and I'm going to stick to this, is very, very, very much so surfaced around the actual person completing the weld, not necessarily their weld procedures, not necessarily their tickets, not specifically all the drawings and all that, them actually doing the job itself. So if their minds are elsewhere and they're thinking about lunch, or they don't feel well, or they're so worried because they've had so many failures that they may get kicked off a job, or somebody's going through a divorce, or a family member is quite ill, they may not be there. I have a very funny story about one of the welders I was working with on some PQRs, so weld procedures. I hooked up my Fluke, which is a control or a volt amp meter that would hook up to my phone, and I could do all real-time monitoring. And the welder and I had worked together for many, many years, and we've done a lot of procedures and mock-ups and all that, so we felt quite comfortable. He was a very skilled welder. And I sent him off on his merry way, and I said, just text me when you're ready for this next step, and we'll go from there. So I come back later, he texts me after lunch, and I'm like, okay, cool, everything's going well. We finished the joint. I package it up and I ship it down the highway to go get destructively tested. A week later, I get the results back. failure. I said, what the heck, this guy's very good. He's never busted a weld before. That's really weird. So I go back and I look at all the data I had, which was, again, my mistake. I should have looked at it up front. And right after his second coffee of the day, which is typically at 10 a.m. for about 15 minutes, after he started welding again, you can see all of the spikes and you can see all the amperages and all that beautifully graphically. And he was pretty consistent. And then there's this huge spike and some other shallow spots and kind of all over. And then he kind of gets consistent again right before lunch. I went over to him and I said, hey man, like last week when you were welding this job, what happened on first coffee? And he said, oh, well, me and my missus, his wife and him had an argument on the phone. I said, oh, I hope everything's all right. And he chatted about it. And I said, well, it's funny. It's not funny, haha, but interesting. And I showed him the graph where you could see all of the consistent nature of his amperage in particular prior to first coffee. Then first coffee happens. And then it's kind of all out of whack for quite some time and he gets consistent through the day. And he said, that's really funny because I was fuming mad and that's all he was thinking about. And he wasn't focusing on the weld. So it's very interesting where the vibe of the welders can become very important on the actual, successful application of a weld itself. Fortunately, that was a weld procedure, not a production joint, but it is important to sit there to do that. Now, do you baby everybody? Not always, but important to at least assess that. Here's my animations. So are all personnel aware of the scope and does it make sense? This is a delayed coke drum repair that I had done. And as you can see on the screen, there is writing and scribble and writing and scribble and writing and scribble and writing and scribble. There is nothing more confusing than a confusing scope. Do people understand what they're supposed to be doing and does it make sense? Just because they understand it doesn't mean it makes sense. Just because it makes sense doesn't mean people understand it. I am a big advocate for sitting and talking with the specific welders on a job, if it's appropriate, of course, and walking them through their scope, because a lot of the time the guys and gals doing the work don't have the same viewpoints as you do. My fiance says it all of the time, and he tries to, broadcast this through the wide public. A lot of welders, and it's not in a condescending sense, a lot of them don't have, a lot of education, and that's fine. Some of them do. Some of them not having education, may be able to comprehend a lot of very sophisticated repairs, and some may not. You really need to sit there and I don't want to say dumb it down, but make it digestible for the people that you're working with. Now, so when you have a very sophisticated repair plan and drawings and fabrication and everything's been well thought about and spelled out, that's awesome. Just because you as the engineer or quality person or owner of the project or project manager understand all of the steps doesn't mean the person actually doing the job does. So breaking it down and saying, hey, do this, use that, here's a cute picture of how I want you to weld it. That might be very helpful. Now, drawing on the sides of vessels and crossing it out and changing your mind may not be the best approach. So sit down and have a conversation with the people or person who's doing the job to make sure that they understand what the job entails and why it matters. A lot of the time when you talk to the welders, they'll get it. They understand. They may not know all the technical nitty-gritty details, but they get what they're supposed to do and why that's important. This particular job, I sat down with the 6 welders, 3 on day and 3 on night shift, and this was a temper bead repair. And I said, hey guys, I know this is going to be really slow, and I know it's really crappy being in this situation, in these dirty coke drums and all this, but we need to do the bead sequencing this way to avoid cracking. And you go through, and you don't have to go through, oh, this tempers this layer, and you get the intercritical, heat affected zone and the subcritical heat affected zone and all those nitty gritties. That they don't care about that. But you tell them and you sit there and you explain it and you say, hey, if you put one bead here and then you put another bead on top and you show them a picture of the heat affected zones, potentially that helps a lot. I know a lot of the guys and gals that I've worked with, you show them, they're like, oh, that's what it does. And you're like, yeah, and this is why it's important that we do the welding in this particular manner. That can make or break your production weld. This particular job, they were not doing a proper temper bead sequencing on the first set. And the management of the refinery decided to leave it as is and monitor it on the run. And then the remainers were completed in the proper sense. And it was very interesting because upon bringing up the unit, almost immediately there was cracking in the area that wasn't completed in a proper tempering technique. And they called the welders in because they haven't quite left the job site to do the repair. And they had said to their quality people, yeah, we thought that was going to happen. You know, that welding engineer, she told us that this would happen. So very important to understand what the scope is and doesn't make sense, because if you just tell people to weld, they're just going to weld what they're used to. So what about those weld procedures, PQRs and WPSs? Here's a really cute example as well of a specific job, followed the weld procedure, had the proper PQRs, had the appropriate welders, and still you had cracking. As you can tell, there's a difference of thicknesses on these two in specific, and this particular piece of equipment operates under vacuum. And so that's where your selection of your consumables come very important, those services. And just because you have a weld procedure doesn't necessarily necessitates that it's going to be appropriate for that specific job. Some other cute pictures of actual welding being completed. In this particular case, this is a process called tip TIG. It's an automated TIG that's still semi-automatic, but your procedure may or may not have those requirements, and you may want to go through that. So your approach matters. This was a very interesting job. This was up in a northern region of Canada, and this is a steam methane reactor in the hydrogen production units. This particular place had a loss of containment resulting in a thermal release on another part of the plant, and they came through and did some opportunity inspections and found some through-well cracking on some of the outlet manifolds. As you can see, it's beautiful cracking. If it was to crack, this is a very beautiful welding, very beautiful crack. Unfortunately, right in the weld, which is what you want in that sense. But we went through and had not just the weld procedure, which was already qualified, and the specific welders that we flew in from the UK. You can go through and do those really nitty-gritty details where you can take a job or a crack or a repair from something like this, having the meaningful application while working with the welders, talking about the bead sequencing, understanding the appropriate consumables, understanding how the weld's going to be done, monitoring it in nature, and going about how you're going to complete this. Obviously there's those circumferential 360, and it's very tight spots below in particular, because you have all these outlet pigtails shooting out. So it's not the easiest place to get to, but that application can make or break your weld in that sense. In this particular case, we had utilized very unorthodoxly, but successfully utilized that crack as the root gap instead of completely removing it, because if we completely removed it, there would have been significant changes on the actual full system, and the owner user was not willing to take that risk. So you can see here, we use specific bead sequencing of a very specific consumable size, diameter, etc., to complete the weld. So there we have the weld completed, and once you complete over those cracking and do the appropriate inspections, we're able to fill it appropriately as required. And I know we're running out of some time, so I'm going to speed up a little bit. But again, this was a very specific job. It is a proprietary material for very high temperature applications. So your run-of-the-mill weld procedure and welder was not going to suffice. I do a lot of work on steam methane reformer outlet manifolds in particular, and that is one of the biggest things, is making sure you have the right welders and that they understand the scope and they have the experience to do it, because these are very sophisticated pieces of equipment that can cause very significant loss of containment. So you want to make sure you do it right the first time. So heat input. This is something that a lot of people talk about in the welding world, either people that understand welding to a reasonable degree or people have no clue about it. I chose to talk on heat input in particular because people throw it around like it's a roll of dice. So is the heat input important? And when do we know that it is important? Because if you do have heat input and it's important, you know, in ASME Section 9 world, your supplementary essential variables are invoked. That means that your toughness is very important, or your low temperature application for your crack resistance. A lot of people want to focus on hardness, but in my experience, and I think predominantly in the metallurgical world, toughness is very, very important. It's your resistance to cracking, and we don't want welds to typically crack. So this may not just be the application of low temperature, just as we saw on the slide prior, which is a high temperature application, which is a high nickel chrome alloy, which you typically wouldn't have an issue with cracking, but in that case you did. So toughness is very important. Heat input can be also important for specific critical repairs, even if it is base metal, carbon steel boilerplate on that essence. But due to the thicknesses, or you know, the piece of equipment, or the aging or service requirements of that equipment can be important to monitor your heat input. Duplex stainless steel, very important for your heat input to be controlled. Temper bead or controlled deposition welding, as we talked about, is very, very important for your heat input. I put here the ASME Section 9 first formula. There are actually 3 of them, and there is an AWS standard. It's B something, I forget. I'll link it afterwards, on not specifically heat input, but power source output. And a lot of people mistake heat input for power source output. There is a vast difference between the two. People will always say, oh, we want the heat input to be X amount of joules or kilojoules or whatnot. But how do we know that's actually happening to the actual weld mat? I have a whole other talk on heat input and power source output if anybody's interested at a later date, because this is something that is truly, truly massively misunderstood, heat input versus power source output. So your heat input practically, again, talking about the people who are conducting the work. These are going to be your welders. Your welders, if you tell them the heat input must be this, a lot of them, not all, but a lot of them are going to look at you like you've got 3 heads. They're going to say your heat, that's your amperage. And a lot of welder terms, that is your amperage. Turn your heat up, okay. Turn your amperage up. Turn your heat down, okay. Turn your amperage down. Where what we would mean in the welding engineering or materials engineering or mechanical engineering aspect isn't, you know, your amps. Your heat input, as we saw in the prior slide, is just one portion of it. You've got your amperage, you've got your voltage, which is essentially your resistance or potentially your arc length, depending on which welding process. And you have your travel speed. To get your heat input to what you actually want it to be, your best approach is to give the welders the travel speed and their amperage. Their voltage, there's not as much control on it, and more manual processes like TIG and stick in predominant. So if you give a welder, hey, this is going to be your amperage range, and this is how fast you need to be traveling with your wire, you will be a lot more successful in getting the actual heat input that you want, or the range of it. I would suggest that whoever is doing those gives those range. And these are very simple calculations. As you can see, my very terrible chicken scratch, you can sit there and find out your travel speeds, you know, ranges 1 and 2 very easily. Now, you'll notice on here that you have, you know, the sizes are very important. You know, what is the size of your consumable being used? Just because you've done the calculation, you know, for 332, fantastic, and you got the range of travel speed and you got your range of amperage, fantastic. Now, when you go out in the field and the guys where they're pulling their rods or wires, they may not have 332 wire or rod. So you need to take that into account too and say, hey, either give them all of their options depending on what size of consumable you're using, and say if you're using a 1/8 rod or wire, use an amperage between here and here, and use a travel speed here to here. If you're using 332, you know, use your amperage from here to here and your travel speed from here to here. That will make a significant difference. Saying the term heat input, you know, you may have some really good welders that understand that, but a lot of the case they don't. So you need to make it understandable for their terms. Again, the sizing, you know, what are those sizes? Are there multiple sizes on a job? Are they using, you know, one 3/30 seconds for the roots, and then 1/8 for the fill in caps. So give them those ranges and help them understand this is the reason why. Having those conversations will make a significant difference on your application of your production weld itself. And then that's how we really get the heat input that's desired. You really want to sit there and understand if that's important, what those ranges are. Just giving a specific one number, 55 kilojoules, you're going to be, you're going to be very much so restricting yourself to that very specific area. Giving a range, which is appropriate, is a lot more important. And I would challenge and everybody to sit there and, have the welders do what I would call a practice or play plate, get a piece of scrap metal, whatever it is, and give them those ranges and get them to dial it in and practice until you can sit there and they hit the nail on the head every time. They get within that range every single time for 3 runs in a row. Perfect. You can go off and do your production joint. That's very, very helpful. Here on a lot of these data sheets, you'll also see all those diameters, your specific, recommended amperages, your ranges, your voltages, and you'll note on here that can alter based off of your position. Are you in position, out of position? Are you rolling? Are you upside down? Again, as we talked about, that can alter from inside a welding shop that's completely temperature controlled to upside down in an FCC unit, out to, pipelines cross country in the mountains. So make sure just because your weld procedure says an amperage range of this or a voltage range of this or a travel speed of this, that you actually dial it in on your actual production piece or production location, as well as welding machine. Say you're using a Lincoln versus Miller or what have you, or different cable sizes, that can be very important as well. So heat treatment. This is kind of a very generic aspect that can become very important. Your preheats, your inner pass, your post-weld heat treatment, and I threw in there a special one, solution annealing. I know the SigmaWeld talked about annealing on there. It's one of my favorite heat treatments. Yes, I have a favorite heat treatment. Your preheat, a lot of you are probably very familiar, is that application of heat to the base metal immediately before welding. In this particular case, the gentleman had a setup of a pear burner, target torch, whatever you want to call it, rosebud, and was welding this component on a roller before he started welding. Your inner pass temperature is the temperature that is previously deposited weld metal or adjacent base metal is immediately before the next pass. That can become very important for solidification, hot cracking. Very, very important for monitoring that for specific austenitic materials, predominantly your austenitic stainless steels. And then going into your post-weld heat treatment, which is your application of subsequent heat subsequent to welding. A lot of that becomes very important for your chromes based off of your residual stresses implied from welding. And your solution annealing is a heat treatment which alters the metallurgical structure of a material to change its mechanical or electrical properties. It becomes very important for those high temperature applications materials that again will prevent a lot of embrittlement phases or cracking in nature in that essence. For your heat treatment methods, I've only talked about 3 here in particular, but there's a few others. So flame impingement, you have induction here, which is kind of a newer thing that's coming to North America. And then you have electric resistance welding or pads or chiclets or whatnot on there, but there's also furnaces. So how you're actually doing the heat treatment. I've done a very interesting job out in Germany for an HTHA or high temperature hydrogen attack job where they wanted to complete post-weld heat treatment on an entire vessel that's been in service for 35 years. We looked at, doing flame, we looked at doing electric resistance, we looked at building an entire furnace around it. So there's many options to that, and don't let your imagination restrict you. Look at all these different things because those crazy ideas might just work. I've done a number of jobs where we've built furnaces around pieces of equipment in the field, which has been very, very neat. A lot of challenging and a lot of work to be put into it, but very doable. So as a summary, we'll look at make sure you look at the intentions of the weld. What are the codes, standards, recommended practices, services, etc. of the weld met. where's welding taking place? Is it the shop, the field? Is it an internal? Is it external? What are the climate conditions? What welding processes are being used? Is it TIG, stick, subarc, MIG, flux core? Do you care about the heat input? Do you have those toughness concerns? Make sure you remember on how to communicate that. You know, what heat treatments are needed and which methods are being used. Are you monitoring for preheat, interpass, post-weld? Are you doing solution anneals? Are you using flame, induction, electric resistance, combustion, etc.? And have you talked to the men and women doing the welding or all the other parties involved? The vibes really matter. It is very important that everybody is communicative, collaborative, they have the skill set, and if they don't have proper training for it, because at the end of the day, you do not want your welds to fail. Typically, you don't want them to fail. Here I've got a very cute quote by Walt Disney, and this was a very interesting job. It was a pilot plant where they sat stagnant for quite some time, and the quote goes, the way to get started is to quit talking and begin doing. So don't just talk about it, make sure you actually have an action or a response to it. And thank you for listening. I think we're probably right at the 1 hour mark.
Yeah. Thanks a lot, Paisley. This was a really wonderful talk. Very basic, very to the point. And we have a lot of interesting questions in the Q&A.
Sure.
So if you would like to take a few of them up.
Yeah, most definitely.
Yeah, so you can, there's a Q&A button at the bottom.
Let's see on there. Q&A. Oh, 25. Wow.
Yeah, and there are a few more in
Yeah.
the chat, but we can start with the Q&A.
All right. Do you all want to select ones and I can just answer them, or?
Just answer them randomly, and whichever you do, we'll just put a tick next to it. If you can go up from the top.
See, yeah, Cameron, what you can do is maybe you can take few of them, and remaining we will be sending you the full questions. Maybe you can answer them and send us back,
Yeah,
which
most
we can
definitely. I
share
can
with
do.
all the participants.
Yeah, more than happy to do so. So an anonymous attendee mentioned, I wanted to know more about WPS and PCAR used to qualify the process of brazing. Be kind enough to elaborate it during the presentation. I will note on that. I'm actually going to ASME Section 9 code committee meetings next week. I'll be proxying for somebody. One of my very good friends, she's the chair for brazing, so I'd be happy to get you more in touch with her. Brazing is not my specialty, but I just wanted to point that out.
I think maybe we can request her for a special session on brazing.
Yeah, she's fantastic. Let me see.
So we will be in touch with you for that.
Yeah. Ankar mentioned he's got a few on here. Number one, has any recommendations or preferred for brands or trade names of consumables? He notes for P91 for TIG and stick. I can send those over, and he's I'm picking all the hard ones that I don't have as much experience on. I see one on here from Ronkel. What is the procedure for renewal of WPQs per ASME Section 9? So in Section 9, it kind of gives some flexibility if you've maintained continuity within 6 months. So if a welder has completed a weld test and was successful and passed, say, on January 1st, and uses the welding process, doesn't have to deal with all of the same base metals or the filler metal or positions or any of that, is purely just the welding process. So if they use, stick or shielded metal arc welding within those 6 months, they can prove a continuity for years. This welder could potentially have taken one test and made sure that he or she had used that welding process every 6 months for 5-10 years. Now, some places don't allow that. That is just the bare minimum of the code of Section 9. Some places, if you're working for a contractor, make or require you to do a weld test before every job that you go on. Say you work for owner user 1, you need to take a weld test. Say you go and do a job for owner user 2, 2 weeks later, you need to take a weld test. For renewals, there's a whole section on there in the QW 300 section on those. You can do a weld test itself. You can do a non-destructive shot on a production weld as well, such as X-ray or AKRT, or you can do volumetric UT on that sense. So you may not actually have to go through and do a full, cut out the bend test, weld test, bend test on that. So those are your options as well. Arnab mentions on how many types one can cut and re-weld the same location in low alloy steel. Is there any limitations per code or good engineering practices? That is a very fun one. I've done a lot of R&D myself on particularly 5 chrome. And the reason why is in our FCC reactors, we use a lot of 5 chrome on the bottom section of the cones, and they go through a lot of repair. There isn't a specific outline that I'm privy to at this moment. There may or may not be of requirements, but we found with our welders on our aged material, we use artificially aged and we use some actual aged material that we were comfortable with. 5 times was our case where we would go through it and not re-weld on 5 chrome in particular. We were able to get it up. I think it was like 8 times in it where we start to see significant microstructural changes, where we actually cut everything up and look at the microstructures, because again, low alloy steels, your chromes, predominantly require post-weld heat treatment. So if you've got weld repairs and you need to do post-weld heat treatment, and then you have a weld repair and you need a post-weld heat treatment, and you do a weld repair and you need to do a post-weld heat treatment, you can metallurgically change your base metal. That kind of leads into as well, like, what is the age of your low alloy steel? I work with a lot of equipment that was made in the 30s, 40s, 50s, and 60s of materials that are no longer in common day production. And a lot of those, which are really interesting, that have been running really hard and very hot and for long times, just because they're supposed to be 2 1/4 chrome doesn't mean that they're actually 2 1/4 chrome any longer. You can get a lot of migration. Your microstructure can change. Depending on how the equipment was operated, can be another aspect too. If it's nice and steady state, fantastic. If you have a lot of upsets and shutdowns and upsets and shutdowns, that can change things as well. It's not very intuitive, but it happens. There's lots of really good papers out there on those. I don't have the paper that I had done to share, unfortunately, because it was in-house to my refinery. But I'd be happy to talk about it further. I see one on hard facing, special place in my heart as well, coming from the oil sands or tar sands in northern Alberta. We use a lot of hard facing for our slurries. This one talks about hard facing PQRs made as per section 9, table QW 453, as mentioned in the PT test. Acceptance criteria is QW 195.2, as mentioned in the code. And his or her question is the hard facing time stress relief cracks appear in the test coupon? How to perform the PT test or a liquid penetrant test, and is the PQR produced without a PT acceptance or not? This is a very fun one because depending on the weld process, predominantly shielded metal arc welding or stick welding, as well as flux core welding, you will get those stress relief cracking or checkered pattern cracking. It's just the nature of the hard facing, especially if you're looking at your 513s, like I'm going to use a trade name, like stellites or studies or any of that. That's just the nature of that material. It will stress relieve at the top, which is really interesting in section 9, is it leaves it open. Unlike corrosion resistant overlays where it has to be indication free, your hard facing, you can depict that in your weld procedure. So you can sit there and do your PQR and you get your checkered base cracking, and you can measure it, on a size, on your thickness and, area, if you will, and say any stress relief cracking within these bounds is acceptable, right? The biggest thing is doing the macros on there to make sure that those stress relief cracks don't propagate or don't go into the base metal. That's the biggest thing. But you can denote whatever you want. If you want to accept stress relief cracks up to an 1/8 inch wide, you can. There's no restriction in the code. Is that good engineering practice? Probably not, because you can sit and get some impingement on those areas and wear it down over time. But you can do that. Internally at my prior refinery, we had come up with a metric after a lot of R&D and testing and mock-ups using the ASTM G65 test, I believe. And we came up with within a certain square footage or inches, you could only have so much sizing and width. I think our widest width was a 32nd, if my memory serves me correctly. And we allowed stress wreath cracking up to or down to 1/2 an inch in size for I think it was a footage in there. So you can definitely depict whatever you want on that. There has been a lot of talk in the Section 9 Code Committee meeting last year in November around this, and it was motion to remove this statement on the PT test, and it was respectfully voted down. So it will remain in the Section 9 code. But I think a lot of people don't interpret it that you can depict in your weld procedure whatever you want. You just need to make sure if you're sending it to your testing lab that they don't say reject. You have to give them that criteria ahead of time, because that will cause you a lot of headache. I'm trying to see what else. Mantu mentions, is it mandatory requirement to heating and cooling rate during post-weld heat treatment as per approved PQR, or shall we use heating and cooling rate as specified in ASME code? Again, that really depends on your application. Are you using ASME as your code of construction? If so, the answer is yes. You want to follow ASME heating and cooling rates on there. If you're doing it for fun out in the garden to weld water troughs, for some reason, if you wanted to use chrome, do you really need to do that? No, you can use whatever you want. A lot of people, to widen their range of their weld procedures, they won't specifically put that in the weld procedure. They'll mention it on the PQR of what heating and cooling rate they used. Sometimes not, because it's not mandatory in terms of Section 9 essential variables. But you can, again, put per code, and you basically leave it up to the person utilizing the weld procedure to go through and verify the code, or have the engineer who's done the work package or design construction drawings to outline that specifically. So it depends on that. How do you select gas mixer proportions? So I'm assuming that kind of goes around the actual shielding, backing, or trailing gas compositions. This is a very interesting one. It really depends on the base metal. It depends on the filler metal. I've done a couple really cool studies on alloy C276 for wire feed in particular, gas metal arc welding with the transfer mode of STT, so short circuiting, and then a flux core. And I've got some really cool pictures on the different gases and everything that was used. But it really depends on what your application is. I will note that ASME Section 2 Part C, if you go to the specific consumable that you're using, normally in Annex 6, sometimes Annex 7, you can go to the specific consumable that you've selected, and it will tell you which gas is most recommended. Again, that's a kind of a rule of thumb. It's not always applicable. I know in a lot of places, like in Canada in particular, people love helium. They love helium. Like helium has got to be in every gas. And we know in a lot of places in the world, A, you can't get it. And B, it can be very costly. So you can play around with those gas compositions. Now, I wouldn't go ad hoc and select things randomly in nature. You should have some intuition and technical basis behind it. And there's tons of information online, or feel free to reach out on those aspects on how to, appropriately select those compositions for whatever welding process, base metal, and consumable that you're using. Do you guys want me to keep going, or?
Quickly, just your email ID. I think there's a spelling mistake. Is it correct? The Republic Testing Labs.
Yeah, it should be Testing Labs. That's correct. I can update that. Yeah,
So
appreciate that.
That's all right. Because people are trying to note it down. I thought just because it should be same as the website below.
Yes, that's correct. I can update that before I send it out to you.
All right. Thanks. I think Krishan, Dr. Krishan, you want to take another couple of questions or?
I think we have already taken a lot of questions and
Yeah.
many
We
more
can-
I think are remaining.
Yeah. What we do, we can share these as an email to you.
Yeah.
And
Yeah.
if you can reply to them, we will share it back with the audience, and hopefully it will be a
Yeah.
good session for
Yeah,
them.
so you could generate a lot of interest amongst the participants. In the peak time, I think, Nimesh, we had almost 170.
Yeah.
in
We had
this
about
webinar
170 people on there.
and almost from, I think, 15 to 20 countries.
Wow,
No,
that's awesome. Very cool. Very
Yeah.
cool.
All right. So it was really nice, well presented, and I think there's a good set of interest generated. And we really thank you for sparing the time and on the Saturday and giving us the opportunity to bring this out to the participants.
Great. I appreciate you all inviting me, and again, more than happy to come back, and I can ensure my fiance comes on a talk too, and a few of my other friends.
Yeah. So
So-
I'll be in touch with you for that soon. Yeah.
Great.
Sure.
Awesome.
Thanks. And we'll get probably more details on, there's a couple of requests for ASME section 9, more in depth on that. Maybe we can have one session on that.
Yeah, for sure. Like I said, I'm leaving on the 12th to go through the week for ASME code meeting out in Scottsdale, Arizona, and I attend typically all 4 every year. So
Wow.
if any, yeah, and there is an international working group in India. If people are not familiar, and I would recommend joining. And you don't have to attend every meeting, but it's good just to know that it exists and attend.
Do share the details. We'll definitely be joining it, and it'll be good.
Perfect. Cool.
All right. Thanks a lot again.
Thank
And
you.
Dr. Christian, to you, over for the word of thanks.
Yeah, we would like to thank Ms. Cameron for this wonderful lecture. And that too on a Saturday early morning. I think we started around 6 a.m. for her.
Yes, that's correct.
Yeah. So we all had a good time, and you can see the number of questions which have been raised. And as I told, we had a good participation across the globe, and even I could see some experts from Nickel Institute.
Yes.
A lot of
Graham.
Graham, and a lot of experts from US.
Yes.
Yeah, perfect. The Nickel Institute is a great one. I have a mentor, Gary Coates, that is the Nickel Institute. He's fantastic.
So we regularly have webinars from Nickel Institute for us.
Yes.
So Gary's been here a couple of times.
Yeah, he's fantastic. I love
Yes.
Gary. He's the sweetest man.
Very true. Very true. Great.
So we welcome you to this small family.
Yes, I appreciate it. Thank you.
Thank you. Thanks a lot.
Thank you very much. Thank you everybody for attending and being a part of the Weld Tech Talks 31. Soon we cover, this year we'll finish 3 years, and it has really generated good set of interest, and it's been a nice place to interact and share welding knowledge. Once again, thanks to everyone and for attending this.
Thank you. Thank you. Bye.
Thanks.